Hello, this is Pat Kelly. Okay, in this problem, what they start us off with here is actually the function for a force field. Sounds cool. But the directions for us are to use a graphing utility to graph the tangents to this force field. Okay, so that's going to get into our differential equation work. So to actually start, what we need is, if they even mention something about the tangents, you want to be thinking dy dx. Okay. So I will begin by trying to find a dy dx, and it's not as involved as it looks, okay, because I'll even add some color coding for you here. The dy in this ratio is actually just all of this component that multiplies by your j vector, okay, and the excuse me, the dx in this ratio is all of this component that multiplies by the I vector, okay? Excuse me. And be careful with this. I did try to make sure my yellow bracket here did grab the minus sign, okay? It looks like subtraction, but think of that as a minus factor of that expression there. So back to my dy dx, this equals one pretty good sized fraction here. But I get my numerator by grabbing the dy expression. So that's minus x divided by that square root of x squared plus y squared. That's all under a radical hat in the denominator there. And my dx comes from what's here in orange, and that'll be y divided by square root of x squared plus y squared. And that's fortunate for us that the denominators of these two are the same, because then they cancel out, and this ends up equaling minus x over y. Okay? All right. It's a good start. And some people might even recognize something that's going on right now is that we get a derivative, a dy dx, slope of a tangent line, equaling a minus x over y. Some people might know what this graph is going to end up looking like. But I'd rather not bank on that, because in fact you definitely want to have a good systematic approach to continue from here if you don't recognize it, because in your other problems it might not be something that you can recognize. So what we do is consistent with the lesson that we've been looking at with finding the solutions to an exact differential equation. Let's rewrite this equation and try to find our capital M's and our capital N's. So this fraction and this fraction, just imagine cross multiplying, right? And so we would get y dy equals minus x dx. All right, just cross multiply. Then in order to make it look like one of our exact differential equations, I'll even bring the x dx to the left-hand side. It becomes positive. And I'm sure you knew what I meant when I said m's and n's, right? And now you see them, is that that would be our m and that would be our n, right? And we like that because then we can try to start getting our answer for that general solution. Let's see, maybe I'll grab green again. I'll slide over here. But we start getting our answer by finding that f of x, y, which I'm sure you know by now. You've done your homework. That's the integral of either m or n. Take your pick, and they're actually equally, I don't want to say the word easy, but they involve the equal amount of work, okay? No shortcut here. And then dx, maybe it was easy, because now you're integrating this guy, and that's actually just x squared over 2, right? Plus, remember with these that you tack on some function of the other variable, so in this case g of y. And we need to find that g of y, so in order to do that, slip down here. You take the partial derivative of your f of xy, partial with respect to the other variable, the y in this case. And so I'm differentiating this expression with respect to y, though, so that blanks out the first term. And the second term becomes g prime of y. And this must equal, this is the case where we say, we set this up, we say it must equal, and then it must equal the capital N, which is just y for us over here. So I'll say it must equal y. So from there, I find g of y by anti-differentiating. The antiderivative of y is y squared over 2, which means my general solution, let's see if I slip over here for my pretty much final answer here. My general solution is your f of x function, f of xy function, which is right here, x squared over 2 plus g of y, but we figured out that that's y squared over 2, equal to some constant. And I'm actually going to put a subscript on that, only because I'm going to take you one step further. This will look a lot neater if we multiply the 2 over, and we'll get x squared plus y squared equals, and I just say c there. The 2 gets absorbed into the constant, okay? So this is my general solution. Just put a quick kind of box around it, because I like that answer. It's a good final answer, but we are going to comply with the directions. Use a graphing utility to plot the family of these curves, which means just different values of c, okay? All right, now, and I was kind of muttering before about, hey, some people might recognize this. Don't feel bad at all if you didn't. What you will get to now is circles, okay? So these are just going to be a bunch of circles of different radii, all right? But we're going to graph this on a graphing utility. I'll grab mine. And the idea with a family of curves is that you're going to have different values of c, really your pick, okay? I'll pick maybe 2 of them. How about a c value of 4 and a c value of 9? I'm thinking of nice circles, a radius of 2 and a radius of 3. But if I start with my c value of 4, I'll go to a graphing utility. And if I'm going to do this as functions, my y equals, I have to break it apart, because as it is, a circle is not a function. And I'll break it apart with my y sub 1 equaling square root 4 minus x squared, close parentheses. And you see what I did is I solved for y. You would know to do that, right, to get it into a graphing utility. As my second function, my y sub 2, I'll put in the negative square root of 4 minus x squared. Close the square root, close the parentheses. And I did mention I'm going to throw in a c value of 9 here. Okay, so I will also do my y sub 3 square root 9 minus x squared, close parentheses. And finally for me, for this problem, a y sub 4, I do a negative square root of 9 minus x squared, close parentheses. Get all 4 of those in the same axes by hitting graph. Take just a second, and I kept saying circles. I know you recognize that they were circles, but if you don't see them as circles right now on your graphing utility, it might just be the proportionality. So I'm going to do a zoom, and I like square proportions in order to see those as circles. Okay, looks good. Conclusion here then is the family of curves here will just be different circles with different radii. All right, hope that helps. Practice some more on your own.